In this video I will present and talk about the virtual platform that I have been developing and using during my master's thesis. So the virtual platform is for testing and developing systems and testing the systems for autonomous vehicles and vessels. And the main idea of the virtual platform is to separate it into three modules. You have a simulation module that represents the virtual world using a game engine as Unity. Then we have a network module that represents the network of the vehicle on the vehicle or the vessel. And the third module is the external module, which can be another system that interfaces with the network module. Let's take a look at the electronic platform for the car that we will take a look at in this video. So this is the Norwegian University of Science and Technology autonomous or perception lab, which has the Kia Niro is the car. The architecture of the electronic platform of the vehicle looks like this. The most important part for our case is to look at the industrial PC, how we can emulate that part, and look at the 4G router, and then we will also look at some malicious actor that has gotten access to some unit on this network. For example, the iPad Pro shown over here. So just to recap, this part would be the network module in this overarching architecture. So more specifically, how would the interface look? We have a Unity module that has a vehicle or vessel. In our case it's going to be a vehicle. Then we have a controller service, and we have a sensor data streaming service. The network module can have a control client or a camera data client. Specifically for this test, it will only have a controller client, but I will show how the camera data client or streaming sensor data client will look. So let's start with the streaming sensor data. This is the simulation of the vehicle. We can interface with this using these services. So to start streaming, I have made a Rust client that can stream the image from the sensor data. It is made in Rust, as I said, and it works as a dash cam, or the camera is placed like a dash cam. So if we have those two over here, and we can see the frame rate is it's around 40 to 70 depending on the hardware. Next step is to look at the implementation of the network module. For this we've been using GNS3, which is a graphical network emulator. So to compare it with this diagram again, we can see that the 4G router has been swapped out with a switch and a router. This is just to make it simple. It's not totally realistic, and won't look too much into this part anyway. Then we have the industrial PC, which will be represented by the vehicle controller Docker container, shown on the right here. And for all of this to be able to connect an interface with the Unity program, the vehicle simulation over here, we're using this cloud, like this cloud function that in GNS3 that essentially bridges the Ethernet, this virtual or emulated network with a physical Ethernet adapter or network on this host machine. So this network is actually already running, so I can open the console of the vehicle controller. So this vehicle controller works exactly like any other Docker container. We can do a ifconfig, and it will show the IP address it has on the network. I can ping the host machine, and it will respond. The next step now is to have this controller using a controller client actually control the vehicle. So all you have to do is, since this is a Python controller, just run it with Python 3 vehicle controller client.py, and then I have to give it the IP address. So 192.168.1.106. Now it's connected, and I can control it with WASD. So if I press W, it will go forward. If I press D, it will turn to the left. If I press A, it will turn to the right. If I press space, it will just idle. If I press X, it will brake. So as you can see, the REST streaming client over here is capturing everything as it should. You can have multiple cameras, but that's really resource intensive, so only the dash cam is included as of now. So this is the core functionality of the system. The next part is how to test. We can test by including an attacker machine. For this case, it will be Kali Linux. So just to represent it properly, we'll add a custom symbol. Be a skull, just to signalize that it's an attacker. Then we can connect it to the switch through the Ethernet 1 interface. Then we can start all of the hosts on the network. And as you can see, you get a warning up in the right here. It's using a lot of resources. This is only done on a laptop machine, so it doesn't have a lot of resources available. And let's log in as root to perform our attacks. The initial step of a penetration test that we will do here is to do information gathering. And as a new attacker on this network, this Kali Linux host might not know of all the other hosts on the network. So hence we can do we can run net discover. The results from the net discover is shown in this picture. Just to save time on this video. The next step is to do an nmap scan command for scanning the container, vehicle controller container is shown here, and the results from the vehicle container scan is shown here. The same command will be done for the host machine. The result from the vehicle host machine scan is shown here. This is a bit more interesting than from the vehicle controller container scan. we can see that it has many ports open, and just to be clear and to save a lot of time, we'll know that port 50,070 and 50,080 is the relevant ports for us. So since we now know that the vehicle controller container does not have any ports open, but the host machine that runs the Unity simulation has multiple ports open, it will we can perform we can do more information gathering and do some exploits. The next step, since the network for this is a unicast, the communication between the vehicle controller and the host machine here is not going through the Kali host. So the Kali host has no, without doing anything, it can't listen in on the messages sent from the vehicle controller to the host machine, and the other way around. But one way we can do something about that is to do ARP spoofing, and error-cap is a great tool for that. So to be able to forward the packets, you have to enable IP forwarding, which has already been done for this Kali machine, and you have to select the right Ethernet interface. For our case, it's Ethernet 1. Then press OK, and then we need to select the hosts that will be spoofed. We can do this by scanning for hosts. It will do something similar to NetDiscover. Here we can see that we have a list of hosts. For our case, we will add the host machine that runs Unity to target 1, and the vehicle controller to target 2. Next step is to add ARP poisoning, so that we poisons the caches of these two machines. So essentially what ARP spoofing does is that it's tricking this machine to think that the IP address of this machine has the MAC address of this machine. So when this machine, the vehicle controller, wants to send a message to this IP address, it uses the MAC address. But since the MAC address for the host machine has been swapped out with the Kali host, it will actually send through the switch to this machine, to the Kali machine. And we will do the other way, the same thing, but the other way with the host machine. So the Kali machine tricks the host machine to think that the vehicle controller MAC is this one, the Kali controller MAC address. So essentially, when a message goes from the vehicle controller, it will go to the Kali. The Kali will forward it back to the host machine. The host machine answers, goes to the Kali machine, and the Kali machine forwards it back to the vehicle controller. That's the essential part. So to enable this attack, we have to do ARP poisoning, sniff remote connections. That's okay. And now the ARP spoofing attack is in place. To prove this, we can run Wireshark. And on Wireshark, we also have to add the right interface, which is Ethernet 1. So we can filter on ICMP, which is the ping protocol. and then we can ping from the vehicle controller container to the host machine. So ping 192.168.1.106, and we see a lot of pings comes here. And to prove that it's not pinging the calling machine, we can do IPA, and we can see that the IP address of the calling machine is 192.168.1.105, so it's not the host machine. In fact, we can do the same here. We can do ipconfig, and one can see that the wireless LAN adapter is 192.168.1.106. The next step is, as an attacker, we want to do some harm. So since the packets are going through the attacker machine, we can listen in on the packets and see if there is anything to be learned. So let's go back to the calling machine. Let's filter on TCP packets, and let's generate some traffic. Okay, so let's press forward. Let's press to move backward. Let's put it in idle, and let's break. Okay, everything has stopped. We can go back to the calling machine, and we can start to look into some of these packets. So the most interesting things are maybe the gRPC and HTTP2 packets, since they are actually a bit weird compared to other traffic. And here we can see in the data part of the packet, we can actually read some of the packet, and it says vehicle controller idle. So that's a bit weird. We can look at more packets further down, and here we see one that is maybe very interesting. It's called the vehicle controller break. Now, just for the sake of for this penetration test, we can imagine that what can we do with this break packet. So for this test, I want to try to prevent the car from braking when a break packet or break command is sent from the vehicle controller, but only when the brake is issued. I don't want to interfere with the car when it's accelerating by pressing W or steering. I only want to cut the brakes when that happens. It turns out that RCAP actually has functionality for doing this. You can use filters. So here we can see a couple of filters that I have written. We will only look at the drop brake filter. So if I open the drop brake filter in with Vim, we can see that we can check if the IP protocol is TCP. We can also check if the destination port is 50,080, which is the port on the host machine that runs the vehicle controller service. Then we can also search the decoded data for a specific string to match on, and we will look at break, since we saw that in a break packet it actually the break string can be found. Then we logs to the console in RCAP that found break, and we're dropping the packet, and then we actually drop that specific packet. Okay, so how do we do this in AutoCAD? Well, it's pretty easy. We can go to filters, load a filter, and add the correct filter, which is drop break in our case. Okay, so constant filter is loaded from drop break. Yeah, that should be the right one. Since the filter has been loaded now, we should still be able to drive forward, drive backward, turn, and all of these things. But if we start to drive, we can drive a bit slowly here. Start to drive, and if I now press the brake, I press the brake now, we should not be able to do anything else. Yes, we can't brake, we can't turn, we can't do anything. So yeah, that was the main purpose of the video. We can see that we can drop the brake packets, and you can't turn or drive anymore when that happens. The success rate can be a bit varied. Sometimes it drops on the first packet, sometimes it just blocks and you can't do anything else. The important part is that it doesn't drop on other packets like driving forward, turning. So you can imagine a car that goes up to maybe 30-40 kilometers per hour suddenly don't have the possibility to brake. That is a very serious thing. So the whole concept of this thesis and the system that has been developed is that you can implement the network on a car, something like have been done here. Then you can introduce some malicious actor into the network, and you can actually see everything happen in real time with the simulation. So yeah, that's the main goal. Thank you for watching.